Hello, my name is Jim Sewell. This is my presentation for a DC motor controller. A DC motor is a rotary electromechanical machine that yields a displacement output for a voltage input. The principle of a DC motor is whenever a current carrying conductor is placed in a magnetic field, it experiences a magnetic force. A stationary magnetic field is created either by permanent magnets or electromagnetic field. The current flows in a rotating circuit called an armature, which passes through the fixed field. The induced magnetic field in the armature is perpendicular to the fixed field. This creates a torque differential. The rotor turns due to the resulting torque. When the armature is in the 90 degrees position, we need to have what's a device called a commutator. The commutator's job is to reverse the flow of the circuit, thereby continuing rotation of the armature. The circuit model is shown in this diagram. The armature winding is represented as having a resistance R sub A. Because the winding is wound around the armature, it also has an inductance L sub A. The back EMF is shown as V sub B as a function of T across the rotor. The fixed field is created by fixed electromagnets. The output of the circuit is the developed torque and angular displacement of the rotor. DC motors are modeled in the frequency domain using the transfer function. The transfer function is the rotational displacement of the rotor over the applied armature voltage. The constant proportionality K in the transfer function represents both the back EMF, which is the influence of the fixed magnetic field, electromotive forces on the electromotive forces in the armature circuit, and also the motor torque. For the purposes of the transfer function, they're both set equal and so are represented by just K. J is the armature inertia and B is the motor viscous forces. R and L are the resistance and inductance of the armature windings. In the state space form, the governing equations can be expressed by choosing the rotational speed and the electric current as the state variables. The armature voltage is treated as the input and the rotational speed is chosen as the output. For the transfer function, we're going to be analyzing, we're going to be looking for a second order response with looking for a specific settling time, which will be discussed next. Settling time will be shown by reaching 98% of the steady state. We'll also be looking for a percent overshoot, which will be shown by the N sub P, which will be how far we go past our steady state. Also will be discussed in the next couple of slides. Motor specifications for this analysis are going to be consistent with projects that we've done so far in class. So our J, our moment of inertia for the rotor, is 0.01. Motor viscous force B is 0.1. K sub E and K sub T, the EMF and the motor torque constant respectively, are both going to be set equal, and at 0.01 the electrical resistance will be 1 ohm and the electrical inductance will be 0.5 henries. The design requirements for the motor we're going to analyze is a less than 2% overshoot, a settle time of 0.5 of a second, and a steady state error of less than 1%. To analyze the motor's transfer function using a PID controller, the PID function in MATLAB was used. The DC motor transfer function was input as a transfer function. And then within the PID controller, there's a capability to tune the PID inputs to match what we were looking for as far as our rise time and our percent overshoot as the outputs from the transfer function of the DC motor. By making adjustments within the PID tuner in MATLAB, we can adjust our PI and D inputs to reach our goals of settling time and percent overshoot. We can see that we got settling time much lower than our target, and our percent overshoot is just under our 2%, which is what we're looking for. From the PID tuner in MATLAB, we can then output our transfer function as a function of k sub p, k sub I, and k sub d. We can see that here, and we see that we have some fairly reliable results. Here are the references used. Thank you very much.